Okay. So as I said, this course is advanced finite element methods, and it's not because the material that I'm going to give you is extremely advanced. Actually, for the most part, we're going to be dealing with just one-dimensional problems. But we're going to look at those one-dimensional problems very well. In a way, my objective for you is to, when you go out and you use a finite element software, most of you will probably do that or have done that already, that you don't treat this as a black box, but you really understand what is happening behind the scenes. And you will be able to do that because you are going to be given a finite element code from me, and then you're going to understand exactly every step of the process, from reading the input that is required to run a finite element example, through the assembly procedure to get your system of linear equations, and then the solver, and then the output, so you can actually visualize the results. That is basically what the finite element code is all about. Well, this is actually art from someone in Spain, and captures very well what we're going to be doing here. So that you see that this object, you have different resolutions to that object. And that is basically what the finite element method is all about. You try to discretize an object, and as you refine the mesh that you use, you get a solution to your boundary value problem that is more accurate. So FEM is just basically, you take an equation, you discretize that equation in little elements which have very simplified behavior, and the objective is that as you refine your mesh, that simplified behavior gets more and more accurate, right? This is called H refinement, and it's one way to improve on your approximation. The other way is just to keep your original mesh and then increase the polynomial order of your approximation, and that's called the P version of the finite element method, and we will also be looking at that in this class, okay? And what you see here is one of the things that we will do, right? Captured in art. We will do something called mesh convergence. So sometimes what we want is to see how the error in our approximation goes away as we refine the mesh. So you would expect that as you refine your mesh, the error with respect to an exact solution gets smaller and smaller, and we will study that error. So later, hopefully, when you grab a finite element package, then you can see how that error goes away, because you can actually predict what would be the exact value of your strain energy, for example, okay? So the course outline, we will start by looking at the standard FEM, and as I said, most of what we're going to do is in 1D, but we're going to go to really deep in 1D. Of course, if you understand the concepts in 1D, then it's very straightforward to extend those to 2 dimensions or 3 dimensions. It's the same thing. But what is important here is to build the understanding, right? If you understand how the error vanishes in 1D, then that same thing applies to 2D and 3D. So we will look at the classical problem of elastostatics in 1 dimension. We will start from the strong form, which is your equilibrium equation. Then we will get from the equilibrium equation the weak formulation, right? Or what some people refer to as the principle of virtual work, or your variational formulation, has different names, which is basically an integral version of equilibrium. So from your strong form, which is basically satisfying the equation pointwise throughout your entire domain, the weak statement of equilibrium is basically satisfying that same equation on average in your domain. So we will look into that. Then we will look at the Galerkin formulation, right? Because once you have the variational form, then you need to define your functions, the functions that you're going to use, right? And those are taken from finite element space. There are other ways to do this, so Galerkin is also used a lot in dynamics, where you're basically assuming functions that are valid throughout the entire domain, and that is the principle behind the Rayleigh-Ritz method. Who has taken Farbot's class already? One? Who has taken dynamics? Okay, Farbot's course, okay? We will look at some theorems. We will see that the Galerkin projection actually minimizes the error with respect to the finite element space that you're looking at. So you see already, you may get scared a bit because I'm talking about finite element spaces and projections, and there is nothing to be worried about. Like this is, you will see as you get into the course that all of this is perhaps mathematical jargon, but it's actually very straightforward to understand. So don't get scared by all of this terminology, okay? We will look at isoparametric mapping. So in standard FEM, what we do is we never work on the physical space, but we actually map the functions from a parent or master element. So all of this stuff we're going to first do in 1D. Of course, we're going to extend it to multiple dimensions so that you build the understanding. You will see that it's basically the same. So besides a few things that you have to do to work on the equations, it is the same concepts that apply to higher dimensions. There is nothing different, okay? So we will look at the strong, weak, and the discrete formulation in higher dimensions. What else? I think I copied twice the first stuff here, so there's a typo there. Okay. As I said, one way to improve on your approximation was to reduce your mesh size. The other way is to increase the polynomial order. So instead of working with just linear elements, you could be working with quadratic, cubic, quartic, and so on. And this is another way to reduce the error. It is a very powerful method because you can actually reduce the error much faster than with the H version of the finite element method. Right? We will look into these ideas when you're working with FEM. The best you can do is to reduce your error algebraically, but with p-FEM you can reduce it exponentially, and that is very powerful. Okay, so if your problem is smooth, and we will look into that too, those ideas of what are smooth problems, what are singular problems. So we will be talking about singularities and so on. If your problem is smooth, then the p version of the finite element method is much more powerful to reduce the error. So we will be looking at also the p-FEM in 1D. You will be implementing p-FEM in 1D, right? And p-FEM in higher dimensions, we will just describe it. I don't think we will be doing that in this course in higher dimensions because it's not that straightforward, okay? So in terms of convergence, we will look at both the HP and the HP combined, and we will look at what are the properties of convergence. So again, if you are given a problem and you want to, you can just run a finite element package on your problem and then get something. But how do you know if that is correct at all? Right? What do you do to see whether you need to refine some parts of your mesh or you need to refine your entire mesh? How far are you from an exact solution? All of these things you are going to be able to understand after this course. That is the idea. And of course, we will look at computer implementations aspects. So I will give you a Python package that is very small, and the idea is that you understand every step of the process. Again, from reading your input towards solving the discrete system of linear equations, and along the way you understand how every other finite element package works. It's the same thing. Okay, and that's it. That's it for the outline. The objectives for this course, you have probably read them in the study guide. So eventually you will be able to get any elliptic equation and get from your equilibrium equation or the equation that describes your particular problem all the way through the weak formulation up to the discrete finite element equations that you can solve in a computer. That is the idea. Understand the limitations of the finite element method and a means to overcome them. And then we're going to be studying this method in very simple academic problems. But of course, the idea is that once you understand what's going on here, then you can apply these same concepts in an industrial setting, like for solving a real finite element problem. Okay? And I will be giving you a finite element program in Python that you will actually use to extend to solve other problems. Okay, that is the idea. So these are the 4 core objectives. In terms of material, The course is based on chapters 2 and 3 of a book that we're writing with a couple of colleagues that is more towards the enriched finite element methods. But in that book, we're actually we start giving a very deep introduction to standard FEM and p-FEM, and that is the basis of this course. There are other couple of books that I recommend. Normally, there is the book of Szabó and Babuška. It's called Finite Element Analysis, and it's a very deep survey on the P version of the finite element method. These were the guys behind the P version or p-FEM. Okay, and then there is a classical book of Tom Hughes on the finite element method, linear, static, and dynamic finite element analysis. This is also a great book. Okay, so if you really have time, because we're giving resources, our time is our resource. So if you have enough resources, then these are the two books that I always recommend people are great books for learning finite element analysis. Chapters 2 and 3 from our book, of course, it's a book, it's a work in progress, so it's not there yet. But perhaps the first time that you read them, maybe you will feel lost a bit. So you're going to have to reiterate one or twice more. But that's it. That's all the material that we will cover in this course. So we're talking about perhaps, I would say, 60 pages. So it's really not a lot. Of course, it's deep in terms of concepts. There are 3 theorems there, but it's not a lot of course material. Okay. I chose the nota bene to post these books, the chapters. The idea is that if you don't understand something, you can always highlight and then ask questions, and then you can also interact in that system. It's a really powerful system. We have used that in the past, and it works flawlessly. What I would like is that you interact with one another, and if you don't understand something, you ask questions. Of course, I'm going to jump in whenever I see fit, but it would be nice that you can interact in this system. So chapter 1, actually chapter 2 from the book, but chapter 1 for this course, which is already the review of the standard finite element method, has been posted in Nota Bene. So if you have not registered, and I know that you have not, because there is only 14 people registered at this point, there is a link. So if you go to Brightspace, that same link is given there. So you can register to the Nota Bene and start reading the material. Next Tuesday, we will start. Next class we will start really looking at the material in that chapter. So it would be nice if you read in advance, so that we can really take the most use of our time. You have a question?
Yeah. Are you to use your student email or your personal?
If you, sure.
I filled in my personal email. But
yeah, no problem. Anything you like, but you need the link to register. That's it. And of course, we will be posting the courses, the classes in the Brightspace. So every time we have a course, then I'm gonna try to record it, and I will be posting those in the Brightspace so that you can, go over them again. That doesn't mean that you can actually take the course by just looking at the classes in your bed, right? It would be very nice if you're here, because then you can interact with the course. Of course, you can do that, but I would really appreciate if all of you are present. Also, I will be posting the recorded videos from the class, and also the PDFs that I get from the notes that I'm going to take. Okay. All of that is going to be in the Brightspace. In terms of assessment, there is going to be only one final project, and it's 100% of the grade is there. So if you understand the material in this course, then you will be able to do that project very well. Actually, the class that you're going to take now, I decided to split my old advanced finite element methods, which was it was divided into these standard FEM, p-FEM, and the enriched FEM. So I decided to divide that because of the number of credits, and I think this is going to work better. So if you are interested in enriched finite elements, you need this course. But if you're not interested in enriched finite elements, then I think this course is going to give you enough material to really understand standard FEM and p-FEM. Okay? In terms of prior knowledge, of course, it would be great if you have some knowledge already on finite element. That doesn't mean that you require a lot of knowledge. If you have ever used a finite element program, then I think it's more than enough. You know how it works. Who has worked with the finite element software? Yeah. If you have never interacted with finite element software, that's also fine. And in terms of programming, we're going to be working in Python. If you want to work in MATLAB, that's also fine. So I'm very flexible, okay? But I really recommend Python, right? Because, well, it's free. You don't need a license after you leave the university. And it's actually a very powerful tool. And believe it or not, when you go to an interview, if they see Python, they say, oh, okay, it's an asset. So for those of you who don't know about it, there is an incoming Python workshop in collaboration with Taylor. This is going to be the 4th time that I give this Python workshop. It's going to happen next Tuesday at 3:45. And after that, there is a dinner. So who is not registered for this Python workshop?
It's full, right?
It is already full.
Yeah.
It was also quite weird because on the advanced FEM Brightspace you said to keep posted, but then the announcement was already made.
Yeah.
Prior. So it's a bit confusing. So
I will discuss with Evelyn and with the people from Taylor to see whether we can move to a bigger room, because that's the only limitation, right? There are 62 people already registered for the course, and no more people can register because of the room space. But if we can find a bigger room, it would be very nice if those people who are taking this course can profit from taking that workshop, because that is something that we will not be doing here. I won't teach Python again here. I'm giving a workshop, so it would be nice if you can take it. So I will keep you posted on this. I will send a message through Brightspace to see whether we can get a higher room. So again, how many people did not register? Yeah, it's quite a lot. How many people did not register and you feel that you really want to take this workshop? Okay. Who knows Python already? Okay. Who knows another programming language, like MATLAB? Well, that is great, because from MATLAB to Python, it's just learning syntax. So if you know MATLAB, you already know how things work, how a program is written. Not really, but I mean, Python is much more, because you have objects, and I don't think MATLAB has objects. Yeah, so we're not going to be dealing with any fancy object-oriented programming in this course anyways. So if you know MATLAB for this course, it's just enough to jump from there to Python. So that's that for the Python workshop. And as I said, this is a course that is required for what I really, really, really want to teach, which is Enriched Finite Element Methods. So I'm going to use a bit of the time remaining from this explanation to tell you a little bit about what is coming next. Because the idea of enriched finite elements is to overcome some of the limitations of standard finite element methods, right? So when are those better? Well, there are problems that require some very complex meshing. And if you have a very complex geometry and you really don't want to be dealing with creating complex meshes, which, by the way, takes about 80% of the total time. So there have been some studies, they basically start timing from the moment a problem is given to the analyst all the way throughout the creation of the mathematical model, the meshing solution, and then doing whatever changes and so on until you get the result. And it turns out that 80% of the time is spent in creating the computational model, which is the object, the geometry, plus the mesh. So in those problems, the idea is to why just not get rid of that 80% of the time? Just use a very simple mesh, and then you transfer that complexity to the actual formulation. And that is what I do for a living, right? That's my research about. Problems that require remeshing, right? Problems where you don't know the final geometry of the object, like optimization, moving boundaries, immersed boundaries, crack propagation, and so on. So these are complex problems to tackle in standard FEM. Imagine you have a crack that is propagating through a domain. Well, at every propagation of the crack front, then you need to recreate the mesh, right, close to the crack front. This is very complex to do in standard FEM. So why not just use a very simple mesh and then let the formulation take care of that crack front that is evolving? So that is the idea behind this. Non-smooth problem with singularities is another. So you cannot really capture singularities with standard FEM. Even if you refine your mesh, you keep refining, you won't be able to capture the singularity because the functions that describe the singularity are absent. So you can actually, we use polynomials in standard FEM, but you can actually add to the formulation anything you want. If you add a singular function to the formulation, then Galerkin is going to tell you whatever you throw through the method is really improving on the approximation because it's going to reduce the error. So you can pretty much throw any function you want. So if you know something about the solution of your problem, you can throw in that function, and then if it is really useful, then Galerkin is going to tell you because the error is going to be reduced. If it is not useful, then the coefficients that multiply those functions are going to be equal to 0 after the solution. So that means, those functions are really not needed to improve on the error. Okay, so in enriched finite element formulations, you can add pretty much anything you want to the formulation, and then you can also see their behavior in singular problems, which is remarkable. And then problems with localized and sharp solution gradients, and I will show you an example of this in a minute. So another thing that you can do, since we're not dealing with the mesh, you can actually use always the same structure, simple finite element mesh. Then these methods are very powerful to come up with statistically significant results. So you can have a problem. Let's say you are analyzing some microstructure of a material that is composed with randomly placed spheres, right? So if you obtain the solution to that problem, then how do you know if that is the actual material? No, you have to come up with many realizations of that, what we call a periodic unit cell, or RVE, representative volume element. So you have to place or pack these particles in many different ways. And then if you think about the amount of work that you need to use the finite element method, the standard FEM, and create what we call a matching mesh at every single simulation is too much work. So why not just use a single mesh and then just let the formulation take care of the different placement of the particle, and then you can run 1,000 of these realizations with just the same finite element mesh. So that is also the power of these enriched finite element methods. Okay. So here is one example where you have standard FEM versus enriched finite elements, and you see basically that for this microvascular network, this was part of my PhD work. Standard FEM requires really meshing the channels, whereas in enriched FEM we can get that implicitly into the formulation and just use a background mesh that has nothing to do with the vascular network. So here I'm showing some other problems. Cracks, we said, some packing of fibers that, again, all of this is mesh independent, or the geometric features of a problem are decoupled from the finite element mesh that you use. Then another problem, everything you see at the bottom, all of this is also mesh independent, right? So you can have some woven composites, or the second figure is a microchannel in 3 dimensions that is also independent from the mesh, and so on. Complex microstructures, again, this is a polycrystalline microstructure, so you see those polygons are actually grains with different material properties, and then there is a crack, and if you want to see how that crack evolves over time independently from the mesh, then enriched finite elements are also used for that. This is also damage. This is showing damage. So for this particular problem, again, some pack of spheres randomly distributed, and I wanted to see what was the damage as you are basically pulling this layer of material in mode 1. I wanted to see how the material evolve the damage. And so what is cool about the simulation again is that all those spheres are independent from the mesh that I use. So you can just place the particles again in random order and then get the simulation again without having to deal with mesh issues. Okay, so that is the power of this tool. And what I'm going to show you here is perhaps to date the most advanced crack propagation simulation. And this is this was done by my collaborator Armando Duarte in Illinois, and that front of the crack from hydraulic fracture, it has very complex physics, and that propagation that you saw is actually again mesh independent, so he's able to track the crack front. This is super hard to do with standard fracture. Okay. And we said something about sharp gradients. So imagine you have a problem where you have a heat that is very localized. So you know that the solution in the application at the point where you're applying the heat is going to be very sharp. It's going to be a very sharp gradient there. So if you want to solve this with the standard FEM, you have to, if you see close to the application of the heat, you have to really mesh so you can actually capture the gradient. But of course, if you're using Enriched FEM, you can not do the small meshing next to the application of heat, but just use a function that captures already that gradient and using a very coarse finite element mesh and still be able to capture the same solution. So these are some of the problems that I am actually interested in. The last one is immersed problems. So imagine now you have an object, whatever it is, and then you want to analyze that object by just immersing that object into a very simple structure mesh. And this is what you see here. This is just the first vibration mode from a beam, but I immerse that beam in a mesh. And to show you that it's truly mesh independent, every frame of that vibration mode, right, has been obtained by rotating that mesh slightly by 3 degrees. So it's very impressive the things that we can do with Enriched FEM. So again, everything that we're doing in this course is to build towards what I'm really interested in, which is enriched finite element methods. I hope along the way, most of you will get the interest, because of course you have to like this stuff very much to get there. But if you're not interested in enriched finite elements, I think you can get off this course by having a very strong basis for just a standard FEM and p-FEM. So this is basically what I wanted to cover in this first introduction to the course. The course is actually going to take, we're going to look at the material next class, partially because I'm still jet lagged. I arrived yesterday from a 1-month vacation from South America, so I'm still recovering. But we have plenty of time to cover the material, so there is not a lot of material. As soon as we're done with the first part of the standard FEM, we will also put up the project. And that's it. That's all I wanted to say. So how many of you are really into numerical work? Okay. How many of you are taking this course because you want to have something about numerical work? Okay. So I assume that the rest are not raising their hands because you're here just for curiosity, or who's here for just know what the heck is going on with this class? Okay. Do you have any questions? Yeah.
In study guide, it says it's a 2-quarter course, and you said the final evaluation would be in the end of quarter 3. So
Okay, that's a mistake. It's a 1-quarter course, and that probably is reminiscent from the fact that this class was divided. Before it was in quarter 3 and quarter 4, and we were also looking at Enriched FEM in the second quarter, right? But now that's not the case anymore. So this course is going to take place only in Q3. Okay, and the idea is that by the end of Q3 you also finish the project. Now, of course, you can wait until the end, but you know that we have limited resources. In our case, it's the time, our resource. So the earlier you start with the project, the better it's going to be towards the end, right? You all know that. So, other questions? Yeah?
Will you be posting a tutorial on installing the Python, but then the Windows version?
I do not work with Windows, but I can try to have someone do that for me. So I will try to do that with one of my PhD students. So who is working with Windows here? Oh my God. Now the question is why?
Cheaper.
Cheaper. So who's working with Linux? Really? Who's working with Mac? Okay, we have our first 10 in the class. Nah, kidding. So,
Do you recommend running Linux on Windows and then Python, or just Python on Windows?
no, you can run Python on Windows. People usually install this Anaconda package that has everything you need to run Python. Of course, I would recommend to run Linux on Windows or run just Linux. But of course, I mean, later on, when you go to an industrial setting, most likely you will be working with Windows, right? Not sure. Anyways, other questions? You had another question?
Yeah. This software package. So are we going to just code Python to code the FEM in Python, or is it like a Python-based script-based software package commercialized?
No. Everything is that package, and it's super small.
Okay.
So, writing a finite element software is really not a lot of science. It's very simple. But you need to know what you're doing, right? So I'm going to provide you with a standard finite element package that is perhaps 100 lines of code or along that. So it's very simple. Of course, you need to understand and study it and understand every line, because if you understand every line, then you see what's happening. And to make it very concise, of course, I have the input is very simple, so I'm using a specific format that you can actually read with one Python line of code. What's one line? Yeah, one line? No, I'm asking. Yeah. Okay. So, yeah.
And will this course or this help us with scripting in Abacus, for example?
Well, once you understand really finite elements, and then you go to the Abacus manual, and then you know what you're looking for, right? So, Abacus scripting is super straightforward, right? Nodes, that's it. Node coordinates, elements, type of element connectivities. We're going to be doing the same here. Now for materials, it's the same. Young's modulus, Poisson ratio. So once you understand this, most likely you will understand any finite element software, because they are pretty much the same in many regards, right? They have different ways of doing the same thing in a way. So, but the objective, as I said, is that you get a finite element software, and you're not just using a black box. So you really understand what's happening. Okay. Other questions? Yeah.
What will we discuss during the Python tutorial next week?
So the workshop next week is just going to be a very simple introduction to Python. So we will be looking at the types of data types that Python has. Those that are mutable versus those that are immutable. Immutable means that you cannot change them when they are created. We'll be doing stuff with the operators like arithmetic operators. There are some other operators that are not standard in other language, like the in operator, some things like that. We will also be looking at so if statements, switch, how to make switch statements in Python, for loops. I mean, everything that you really need to program. So by the end of the workshop, you should be able to program something very simple. Procedural, right? We will not be looking at any object-oriented programming. But procedural code, you should be able to do something towards the end of the workshop. And of course, Python is a scale, so the more you work with it, the better you become. In fact, what happens usually is that after 6 months of working with Python, then you look back at the first codes that you saw, and then you say, how could I have ever written something like this? Yeah, so it's a skill that you build. And of course, it would be nice if all of you who are taking this course use Python so that you build on that skill, and you can actually put it on your CV at the end of the course. Okay? Questions over here? No? It's all clear? Here? That's it? No more questions? Okay. There was something else I did not discuss, which is office hours. I'm still trying to figure out what is the best time for me to have office hours, but I will have 1 hour, 1.5 hours per week so that we can meet and discuss things that are not clear from the course or whatever you want to discuss with me, okay? All right. Well, that's it for today. Next class, we will really start with the material. So please make sure that you read at least the first part of that chapter that I put in Nota Bene. And if you don't understand something, you can start using the system to ask questions, and I will jump in if something is not clear. Okay? Thank you so much.